Welcome to the Digital Amateur Television Experimenters Night. This is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. Do you realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world? Also participate in the night by coming up to the Queen's Domain club rooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30pm local time. We'll see you soon. This is VK7OTC.
Okay, this is VK7OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. And I have Rex VK7MO, who is a regular contributor.
Thank you.
In the studio. How are you?
Thank you, Justin. Yes.
What have you been up to?
Well, when you said, how are you, it sort of occurred to me I should repeat what was happening at lunchtime today, where people were talking about people who have or are about to get an OBE.
Yes, that would be over bloody 80.
That's right. And it is amazing how many of people at lunchtime are either got or about to get.
Right. Okay.
And I'm one of the
So this year is the OBE?
No. It'll be January next year. So
Okay.
I'm 11 months away.
Okay.
Yeah. So, but I'm still going fine, so that's good.
Excellent. Excellent.
Other than that,
maybe we could have 80 on 80.
Not with me, mate.
Anyway, yes.
All right. I think you were going to have a look at DUBUS, weren't you?
We were. Now, DUBUS, which is the fourth quarter DUBUS, so it came out for December of last year. There's been some problems with distribution,
and the second quarter as well.
Correct. Well, actually, that was right. That was because that was the one I got, and
I didn't.
And nobody else got, and it was just bizarre.
But I did ultimately get it.
Okay. So fortunately, what they've done with quarter four, which seems to be suffering from the same issue, is they sent out an electronic copy of it. And when I went through the electronic copy one, I saw that there was an article, and if I go to here, we find that there is an article on optical communication with FST4 and FST4W by Rex and Richard VK7ZBX.
And that's right, and Richard's actually inside. He should be here.
Come
in, Richard.
Yeah, Richard, if you're listening, come in. So take us through. This is the cloud bounce using FST4 and FST4W.
That's right. And I guess most of our testing has just been done between Richard's place and my place, which is 22 kilometres. And we've learned a lot about it from that. But on this particular occasion, Richard went to Mount Wellington and I went to
White Hills.
White Hills. And you can see Mount Wellington's really good at this right-hand end. White Hills it's got a reasonably good takeoff, but it's not very high. And we got signals over that 153 kilometre path of minus 13 dB.
Not bad.
Which is pretty strong.
What period? What?
In 60 seconds.
Oh, okay. Okay. Yep.
Actually, signal strength doesn't change. Reported signal strength doesn't change with period because it's the signal strength.
Yeah. Okay.
But the how far down in signal strength you can decode increases if you go from 60 to 120, etc.
Good point.
There's two charts there. The second one is actually a shorter path between me still at White Hills, but Richard went home, and you can see he has got one hell of a obstruction in the way.
Not only Mount Wellington, but what Coin Mountain or whatever it is here, and plus another one.
I don't think that's Mount Wellington. That's because Richard's at Tea Tree, so he's north of.
Oh no, of course.
Yeah, so that's probably Mount Coin
in the middle. Yep.
No, near the middle is somewhere in the highlands up.
Oh, okay.
I suspect.
Yep.
The interesting thing was the signals now only dropped from minus 13 dB to minus 14 dB. Despite this dreadful takeoff.
Correct.
Now, admittedly, the distance is a bit shorter.
Yeah.
But I think that proved to us that it had to be cloud bounce because the only way Richard could get a signal to me over that sort of obstruction
is with stuff that's up here.
That's right. So we found that pretty good.
Yeah, okay.
With some of the tests we did between Richard and I at his place, we got down to, I think, 20 milliwatts of light. And for that, we had to run the longest period, which is half an hour.
Yeah, 1800.
Yeah. 1800.
Yep.
And that works down. We had some indicated decodes of minus 45 dB.
Ooh. So that's the lower limit, isn't it?
It's a bit hard to say what the absolute lower limit is because when you're so far down in the noise, it depends on whether the noise happens to be in phase or out of phase with the signal at the time it's reporting.
Yeah.
So the same level of signal can report anywhere plus or minus 2 or 3 dB.
Yep. Okay.
But on average, it certainly works. Joe's done tests which show it works on average to minus 44 dB.
That's pretty impressive.
It is impressive. You have to wait a long time.
Worth the wait.
But that's right.
Well and truly worth the wait.
Now, without going too much deeper into that, I will divert to some later information.
Let's come back to here.
And what's been happening since then, and I spoke about it a few weeks ago at one of your sessions, is we found that particular test of 153 kilometres, minus 13 dB, was done with exactly the same systems that we used 10 years ago.
Yep. Okay.
Luxian transmitters.
1 watt Luxians.
And not with the Cloudburter lenses. Just with the broad...
with the single lens.
Torch lens, about 10 degrees beam width. So, since that time, the art of LEDs has advanced dramatically, and we tested a number of new ones, mainly a Rebel of different wavelengths and a Cree of different wavelengths.
Okay.
And we settled on a Cree on a wavelength of, I think it's about 660 nanometers.
Okay.
It's a bit of a compromise between the longer the wavelength, the less absorption in the atmosphere, but my APD drops off in performance as I go.
Yep.
And at this time I don't know of any large area APD, and you need a large area to pick up a lot of photons.
Yes, a lot. Yeah.
That actually works at infrared. So
Okay.
that's where we settled, and the tests we've done show that these improve the system performance by a little over 20 dB to what we used 10 years ago.
Wow. Okay.
Now, that's only 10 dB in light terms because of what we call the something for nothing law, that optical detectors work on current, and current squared versus power, and its signal to noise ratio is the power, etc. But 10 dB in light intensity is dramatic.
Well and truly.
And giving 20 dB
The improvement.
of improvement is spectacular. Now, we haven't tested them over that long distance. I'm still putting together a slightly more LED, a 96 LED array compared to the 60 that we had before. Well, it's more than slightly more.
Just a bit.
Yeah. And
Have we come up with a name for it yet?
no.
Cloud vaporizer?
Maybe, yeah. So we started testing it, and within about the first 30 seconds, half of the... We had one frequency on one half of the array and one on the other.
Slightly offset.
So that we could compare different elevations on each array. And within about half a minute of the first test, one of the arrays stopped working.
Okay.
And that came down to which I've always thought were wonderful little devices, but I now have reservations. Oh,
Hang on. No,
I've already taken it out. That came down to these devices. These are IRF 1405s.
Okay.
And the specs actually say they're capable of 169 amps.
In a TO220, yeah, right.
Now, I can't even believe that the pins would carry 169
Maybe the case would, but I doubt that's about it.
amps. And I've read the specs a few times. I can only think that they handle 169 amps peak for a very short period. For a very short period, and when we started running it, an interesting property of these sort of MOSFETs is their resistance is very low, but it increases with temperature. So it sort of has a high potential for thermal runaway, because as soon as
it gets warmer, it's going to go up in resistance, which means it's going to dissipate more.
And I think that's what happened.
Okay.
Now, we were only running it at 32 amps peak.
Yeah, okay.
Or 18 amps average.
Yep.
And
were they getting warm? Were they?
Yes, it obviously got into a thermal runaway situation. When I say it popped in the first 30 seconds, maybe Richard had it on before I was listening.
Yeah.
And
okay.
Richard said the heatsink felt really hot.
Yeah, okay.
So the question, the solution would be, instead of running one of these for 48, because we were going to run a pair of them, one for the 96, is go back to running, splitting the thing into 4 bays.
Yeah. Okay.
But even so, I'm sort of worried that they're really not reliable enough when we're running a lot more current than we were in the past.
Yes.
And got away with it.
Yep.
So I searched the web for something that might handle more current.
Okay.
And that's what it looks like.
Flippin' heck.
Now the leads look a bit more promising.
Yeah, just a little, and there's the base there. So these are still FETs. These are
yes. You talk about that. Mike.
Okay. So we've got a being still a FET. We've got a source, a gain, and a source, a drain, and a gate. So these are.
Pusher in the back of my
N-channel enhancement mode, fast intrinsic diode, avalanche rated. So we're talking about still fairly low voltages at 100 volts, but we're talking about the ability to switch 200 amps.
Now, I must say, I think these specs look a bit more sensible because they actually quote a spec for the external lead current limit of 100 amps.
Oh, okay.
At RMS.
Yeah, okay.
And then the 200 amps is at 25 degrees C, but I think that's got to be pulse, because if you can't get more than 100 amps through the leads...
No, the next one down. Because that's 25
pulse 400 amps.
So that's 400 amps.
Well, I don't know how you can put 200 amps through something if the lead can't take more than 100 amps.
Well, you can't, because the lead's not supplying 200 amps.
Yeah.
So, yeah, okay. No, okay.
However, so the plan is to
Impressive.
to make sure that we've still got a reliable system, to use 4 of these,
Okay.
split them up between bays of 24,
Okay.
and with...
You can put decent heatsinks on them too.
that's right, and heat sink it properly.
Yep.
We heat sink those properly, but
Yeah.
there's a limit to how well.
You've got a much greater surface area on the back of that.
That's right. I can't work out from the specification whether that is isolated from the terminals.
Oh, multimeter will tell you that.
So, yeah. So
Okay.
the plan is to use these. They are certainly more expensive. These are $5.65, and these are $27. But,
Yeah, okay.
But for the sake of having a reliable system, if you go the trouble of trying to work it.
They're the same as what I use on the 630 metre transmitter.
Oh, okay. Yeah.
They switch fast enough that you can up to 470 kilohertz. So, but you can let the smoke out real quick.
Well, we've already done that too. Yeah. Okay. So
oh no, cool. Well, we look forward to the 96. So, have you received the remaining lenses for the 96?
Yes, I've got the lenses. In fact, when we did the test where this blew up, that was with all the lenses.
Okay.
I haven't yet built. I want to build a new driver unit for these.
Okay.
And I've sort of got diverted into Q65.
Yes. Okay. I can understand that.
But at some stage, we will be in a position to start testing these out.
Fantastic. Well, look forward to seeing it, Rex. Well and truly.
Okay.
Well and truly. There we go. Fantastic.
Okay. Thank you, Justin.
Thanks, Rex. And good luck. And we look forward to seeing the 96 in action. The cloud vaporizer.
I think it's going to be more a bushfire indicator, or confuser.
Yeah, the red glow on the horizon.
Okay.
Very good. Thanks, Rex. All right. Now the just a quick recap of we had our Reast AGM annual general meeting on Sunday. For those who haven't found out by now, the committee and the ex officio positions all are exactly the same, and we're in a good financial position due to a few things that happened. So yeah, we're travelling reasonably well and have some plans to go forward with in 2021. So watch this space. Now, I have been for a little while working on a couple of manual. I can hear the gasps now. Manual antenna tuning units. And I've been doing some research just of late around the different designs and the areas they cover, and what's considered to be an efficient and an inefficient antenna tuning unit. And just I have some interesting observations to make, having now done a little bit of research into it. I have both the RSGB handbook, a reasonably recent one and also an old one, 1960s one, and I also have a number of the ARRL handbooks, and so of course, and the ARRL antenna handbook as well, and so they're the first port of call. And I just make an interesting observation, because historically I think both sides of the Atlantic went down a different path, slightly different path, ended up with the same result, but slightly different path to get there. The ARRL and their antenna handbooks, and I went back through all the way back to sort of a 1960s, late 1950s handbook, all talk about there being a transmatch design. Now, a transmatch design, I dug out a few things here. There's a wonderful article called The Ultimate Transmatch, which, and in fact there's even a better design here, a better article. Of course, there's a whole lot of articles on the net. So if we head over to our close-up cam and zoom out here, you can see this is one of the designs, the SPC Transmatch, and you can see there are two verniers here, and there's a rotary vernier here. These are capacitors, and then there is a rotary inductor in here, and a way of switching it. And if we look inside the box, the next picture, you can see this is obviously built for reasonably high power. And there's the vernier, the front panels, the verniers for the capacitors. There's a large capacitance here, and then this one's split into two due to the way the circuit works. But and then there's a roller inductor in here, and a little ballon hidden away underneath this this rotary switch here. So the ARRL definitely went down the path of fixed inductance, or at least tapped inductance. And so it's just, and here's another example. This one has an SWR meter built in. You can see there's a little SWR bridge here, and there's a meter there. Two capacitors, the roller inductor, and then these capacitors here. Now, I started on down this path quite a while ago, and in fact ended up with two roller inductors. Would you believe? This is one of my old man VK5TWs. He got this somewhere, I don't know where. This is all ceramic. It's on a ceramic former. This is silver coated wire, although it's pretty tarnished. And there's a roller here that literally rolls along the inductor. Sounds like a you're strangling a cat, but anyway. And this gives you, I think, probably in the order of I don't know, 0.2 or 0.3 microhenries. It would be something like that. I haven't actually measured this one. I've measured the other one, but this is reasonably high power. Can take a fair bit of heat and current. Now, the one before I got hold of that, the one that I actually bought to use is a slightly smaller version of this. A very nice little one that actually came from TTS Systems from Dave VK3JKY from Dave and Chlorine, and this beautiful little one. It's again all silver coated. The same arrangement. This is on a like a Bakelite former, a cloth former, and it just rolls along. You connect up to one of these and connect up to the shaft, and you have up to, and I have actually measured this one, up to 0 to 19 microhenries. So 0 to 19 microhenries on this one. It has a very nice little stop at the end that stops you rolling the roller off the coil. There's a little tag that sticks out here, and it ends up against the roller, which is quite a nice little arrangement. And of course, it is smaller, which is relatively easy to mount. So this is a modern roller inductor specifically for antenna tuning units. So then I started looking at, that was the ARRL side of the Atlantic. Then I start looking at what the RSGB suggests. Well, the RSGB went down the path of a Zmatch. Now a Zmatch, probably a good example, hang on, let me just bear with me. A little Zmatch antenna tuning unit, very similar to, this will do. So you can see here, Zmatch antenna tuning unit, they actually, a little bit of the history of it, where the idea came from was, in valve power amplifiers, the way that they would match the reasonably high, and we're talking thousands of ohms of impedance on the output of a valve, on the anode of a valve, they would directly connect to the anode of the valve a coil, and then they would have another coil inductively coupled that would come off with the in this case the from high to low impedance, and would end up giving you your output impedance on the amplifier of 50 ohms, and that impedance transformation was done by these two inductors that were inductively coupled, so these two windings. What they did was then take that idea and put it into an antenna tuning unit, they very successfully came up with what the RSGB called, and a whole lot of the UK experimenters called, a Zmatch, or an impedance match. So this idea then sort of developed, and there were some improvements made to it, and in fact in the RSGB handbook it actually talks about Louis Varney, was G5RV, which is the 102-foot dipole creator, and he took a look at the original Zmatch and went, I think I can improve this, and ended up with with some additional taps on the inductors to get a much better match but there's a very interesting statement in the RSGB handbook, and it's one of the more recent RSGB handbooks. There's a fascinating little statement by Louis Varney, which is he concluded that it was a great multi-band tuner. However, the traditional link inductor coupled antenna tuning unit, which is you have a tapped either a variable inductor or you have a tapped inductor that you switch between. The link coupled antenna tuning units was overall better and more efficient. And I find that fascinating. So to give you an example, I've got, and I don't think I can put this underneath maybe we'll try. We'll just try here because I don't think I can zoom out far enough. Wide. Yeah, can't quite zoom out far enough, but you can see this is RSGB design Zmatch that my old man put together a while ago, and you can see this is a number of concentric coils. So there's an internal coil that's slightly smaller diameter, and then there's an external coil which is of wider diameter, and they are inductively coupled, and there's two sets of them. There's a little set here, and then there is another set over here, and there's two sets of variable capacitors here and here, and you can switch in additional capacitance or not through a switch on the front. And I'm not sure I can turn this around. No, I'm fighting. It's not quite big enough, but what I can do is we can zoom in on up, and now we do a little bit of a focus here. There we go. Okay, so and zoom out a little bit there. Okay, so you can see the two variable capacitors on either side, the loading and the tuning, and then there is a switch which goes on 10, 15 and 20, and then over to 40, 80 and 160. The transmitter receiver is 50 ohms feed unbalanced, and then you've got your arrangement here where you can go from an unbalanced coax feed to a balanced feeder by undoing this link, and then going across here to accommodate an unbalanced feeder, so a ribbon type feeder. That's the construction, reasonably heavy construction. You could the plate spacing here would take, I think, at least probably 300 or 400 watts before it flashed over. So anyway, it all built up into a nice aluminium case. I did note that this little sticker just here, I don't quite know who put this on here, whether it was Dad or not, but this article has been produced to comply with the requirements of Australian standards under a system of supervision, control and testing from the Standards Association of Australia. So I think someone might have been having a bit of a joke there, but anyway, that's a traditional Zmatch coupler, and it relies on that coupling is what enables you to match match the impedances between the antenna impedance and also the transmitter, the 50 ohms that you're wanting to match to, and it is still well and truly in use. There is that design of coupler is well and truly still in use. Now, a South Australian, Lloyd Butler VK5BR, who I think is still alive. I think Lloyd is a member of the Adelaide Hills Amateur Radio Society, like I am, and he had a bit of a think about the Zmatch and came up with what is now a very popular single coil Zmatch, so a simplified Zmatch and we'll zoom in here. This is the circuit of his simplified Zmatch, and I have built a couple of these, and they are successful. They do work. They work very well. So literally there is a single coil, single large coil. Again, you do the same thing. This coil goes around the other coil in the same arrangement, so they're inductively coupled. There's a little additional loading inductor here that you put in for the lower frequencies, I think, from memory. And then your variable capacitor, these are ganged here, and then there is another one over here, and a little coil, and literally that's the whole single coil Zmatch. Very easy to make. In fact, the article, the wonderful article by Lloyd, even goes into the coil former. Let's go wide here. There's the coil made up with the lower number of turns around the outside. You can see here, and then the former here. So you wind your coils through the coil former, perspex support, and I have built a couple of these, and they work very successfully. So that's a little bit of my my adventure with antenna tuning units, and as it gets built and gets tested, I'll have an update in the not too distant future. Of course, any of those coils can be, if you're talking about QRP type of levels of power, you can certainly convert those coils to toroids and wind them on toroids, so you can actually make, and in fact there is a couple of those designs, there we go, into a very little case. That uses some broadcast type, hang on, let me go do a tired and zoom in here. You can see the inductor is a toroid, and the capacitors are little broadcast variable capacitors with the mica plates. So all built into a really small little box, complete with that comes complete with a little SWR, one LED SWR meter. So you can tune for maximum brightness on the LED when you actually have the tuning matched. So quite a nice little unit, that one. So but lots of designs. But it's just I just wanted to point out the interesting observation of each side of the Atlantic going down quite subtly different pathways. So there you go. Now, let me go back to my script. I've probably gone way off of it. Now, reminder to everybody who participated in the Rosshull Memorial Field Day, please put your log in before the 19th of February. That's the deadline. And you can email your log, so you can print it out. You can export it to a text file, or there are a couple of other formats that are accepted. To a text file seems to be the easiest, and email it to rosshull, or one word, at wia.org.au, and you'll get a acknowledgement of the submission. So please put it in if you did participate, because we want to get the participation rate in VK7 up from what it usually is. Now, I've been regularly reporting about WSJT 2.3.0 and the release candidates that have been fairly regularly updated just of late. Well, 2.3.0 has been released as a GA release, which is a general availability release. So it is available for download on the on K1JT's site. They made a comment in those notes that 2.4.0 is due for release soon. So those hanging out for Q65, It's certainly on its way, and at least with the general availability release of 2.3.0, you won't be updating every couple of days, which is what the RC versions were getting us to do because they were expiring. So the GA release is up on the website. Now, next week we don't have a DATV Experimenters Night. That is because we have our February presentation night, and we are lucky enough to have Dr. Mike Groth, VK7 Mike Juliet, giving us a presentation entitled Listening to the Planets. Now, I'll read out the promo that goes with this, because this is fascinating. Decametric radio emissions from the planet Jupiter were first identified by Burke and Franklin whilst they were calibrating a 22 megahertz antenna array in Maryland, USA in 1955. This was later confirmed by data collected by Alex Shane in Australia some 4 years later, and opened up a whole new field of planetary astronomy. The talk that Mike's going to give us is a brief outline of the early history of decametric radio astronomy and how observations in Tasmania and New Zealand between 1971 and 1975 provided the first dynamic spectra of the Jovian radio bursts, so the radio bursts from Jupiter. In true Anzac tradition, all this was achieved on a shoestring budget and using an early generation of domestic videotape recorders in a way their manufacturers never intended. So this should be an absolutely fascinating talk by Mike. This is the subject of Mike's physics PhD. We're getting it from the horse's mouth, as they say. So this should be an absolutely fascinating presentation next Wednesday night up here at the club rooms. We will be streaming it and we will be recording it. There will be the streaming and the recording of that particular video, and will become available on the Reast YouTube website. So. And hello to Harry VK7HXT. I think it is, not XHT. Maybe it is X high tension. Now our videos for tonight, for our RF viewers. The first one is Introduction to Optical Communication for Satellites, This is they're starting to experiment with satellites and using line-of-sight optical communication up to the satellites so that they can get pretty decent bandwidths between the satellite and the Earth station. So this is a bit of a talk about how they do that. There's a couple of talks from FranLab who we had last week. One of them absolutely fascinating about those big displays that sit up in front of mission control, NASA's mission control. She's done a whole lot of research on how they actually work, and it is fascinating. They are big projector screens. It is glass slides. It is where it's projected from is the equivalent size of mission control back behind those screens, and they called it the Bat Cave. So absolutely fascinating on that one. Another one around, there's a 1950s teleregister pneumatical display, and then we finish off with a funny one. We might get to this or we might not. We might run out of time. But a very confused Canadian investigates Australian English. So that's a bit of a funny one to finish off with. But anyway, that's our... Andrew Elwell, thank you. What time will the talk start? 7:30, Andrew. 7:30, our normal start time. And yeah, it's you can certainly come up to the COVID safe club rooms, or you can check it out on the Reast streaming channel, or check it out afterwards, because it will be recorded and put up onto the Reast YouTube channel. So thank you for clarifying that. 7:30 next week, so there won't be a DATV night, but there will be a presentation night on listening to the planets, listening to the very fascinating noises that come from Jupiter, from someone who did their PhD on this particular subject, so Mr. Dr. Mike Groth. So privileged to have him along and giving us a bit of a talk. Anyway, we'll finish up at that. We're finishing up a little bit earlier than we normally do, which is fantastic. We can go and grab a coffee and see what's going on out in the club rooms. Oh, no problems at all, Andrew. Look forward to seeing you, and definitely you're welcome to raid our tea bags, so not a problem at all. Anyway, we'll get underway. 73, and we'll catch you in a fortnight's time for our next DATV night, and in the interim there'll be a presentation night next week. So 73, and have a fantastic week.